Ugh. Okay. So left off last week, Monday, which is a week ago now. So let's go back and let's quickly swipe through these as a recap. All right, so all kinds of different everyday things are acids and bases. And right, citric acid, acetic acid. Acids make things taste sour. You have litmus paper, which is the way that you test whether something is an acid or a base. You know, acids and bases can be used as cleaners or fertilizers. I don't know what bases usually are. Bases turn red, litmus paper blue. Household objects. So let's get to the definitions. All right, so common sodium hydroxides. Oh yeah, we talked about those. We had this one definition, this first definition where acids produce hydrogen ions. And then those are always combined with water to make hydronium. I'm writing the molecular formula. Right, yeah, the ionizable hydrogen comes first if there is one, so all acids are always hydrogen first. Or at least these ones are. Bases produce OH ions in solution. And by the Arrhenius definition, they directly produce hydroxide. But, oh, and then that combines, so if we combine acid with a base, we get water. Bronsted-Lowry definition is better. So acids are proton donors, bases are proton acceptors. So that covers things. I was on that slide. That covers some bases that don't directly produce hydroxide, but do so indirectly. So now you can have hydrochloric acid, produces this proton, which is the positively charged hydrogen ion. So then, yeah, ammonia is one of these where if we add ammonia to water, it produces hydroxide, but indirectly by taking a proton from water. So our acids, proton donors, bases, proton acceptors. We also have this idea of the conjugate base. Oh yeah, conjugate acid-base pairs. So on the reactant side, if you have an acid, on the other side is going to be a base, and not just a base, but the conjugate base. We also talked about amphoteric compounds and how water is amphoteric. So, you know, water gain a proton to become hydronium, or it can lose a proton and become hydroxide. Drew some conjugate base pairs. Look at more of those. These neutralization reactions are always an acid and a base. They produce water and a salt. Sometimes we can produce gases. Okay, I think that brings us back up to where we were. So this was just writing a reaction out. So if you're given phosphoric acid and sodium hydroxide, then you combine those two, and your salt is going to be the anion of the acid and the cation of the base. And then the other product will be water. Acids can also dissolve metals, though. So if we add magnesium to hydrochloric acid, which is if you take Chem 20 as a reaction you do in Chem 20, and you produce hydrogen gas, along with a salt. Sulfuric acid plus zinc will also produce hydrogen gas and a salt. But not all metals react with acids. These are just some examples. So acids react with metals in a way that causes metals to go into solution. So they dissolve. After the reaction's over, they'll be gone. The reaction between an acid and a metal usually produces hydrogen gas and a dissolved salt containing the metal ion. Acids can also react with metal oxides. So instead of having the pure metal, we have now the metal combined with some oxygen, and it produces water and a dissolved salt. So you can see here with potassium oxide, magnesium oxide, both producing water as one of their products, but again, always a salt. All right, so if we want to react hydrochloric acid, it's HCl, plus strontium metal, what are our two products going to be? Or at least one of them. Cool. But one of our products is going to be hydrogen gas. Part of the reason you know that is that we don't have, so in these metal oxide reactions, there's always an oxygen which comes from the metal oxide that combines with the hydrogens to create the water. Otherwise, you just have H2, and that's your gas. So hydrogen, which is a gas, and then we'll have strontium chloride, which is our salt. And these are fundamentally redox reactions, although I don't think we've talked about redox reactions in this class, or so very briefly. So a reaction of hydroiodic acid with barium oxide. Hydroiodic acid plus barium oxide. Now what's one of our products going to be? Or what will both of our products for that matter? No, we're going to get, because now we have oxygen for the hydrogen to react with. We're going to get H2O instead of just hydrogen gas. We're also going to get our salt, which is barium iodide. So it's the anion from our acid. And so our acid is providing the protons. This isn't a base, not in the sense that we've looked at bases, but we're going to take the barium from that as a cation to get our salt. The most important base reactions are neutralization reactions, which we might have already covered. This is from these slides are from Chem 20. The only other kind of base reaction covered in Chem 20 is a reaction of sodium hydroxide O with aluminum and water. Yeah. So not many metals dissolve in base or basic solutions, but aluminum is one of them. So we get sodium hydroxide reacting with aluminum plus water to give you this sodium hydroxide complex and hydrogen gas. And for the purposes of this class, I mostly want you to be able to identify an acid, identify a base, know the two different definitions. So there's the Arrhenius definition and the Bronsted-Lowry definition. So know those sorts of things. And then be able to predict like a neutralization reaction, what the products are going to be. All right, so you're going to get water and let me scroll back to one of those. Just a basic neutralization reaction. So like this one, for example, this one's a little tricky because phosphate has 3 hydrogens. So you need to react with 3 hydroxides to produce water. So that's the kind of thing that I'll ask for Chem 10. That would be like a higher difficulty question for this class. Okay, so aluminum though dissolves in base. I might ask you a question about titration as well, because those are ultimately neutralization reactions. Titration is a very convenient way to quantify how much or quantify the concentration of a solution. Doesn't have to be an acid, doesn't have to be a base. In this class and in Chem 20, primarily acids and bases. But the core concept is that we have a substance in a solution of known concentration, and we react that with another substance in solution of unknown concentration. So our net ionic equation for the reaction between, for example, if we're using hydrochloric acid and sodium hydroxide, would be we're adding protons, or it could be the hydroxide, we're adding the base, acid or base. And as those combine, they neutralize to form water. So if we added, some number of moles, let's just say we add 1 mole of acid, and our solution becomes neutral, then we have 1 mole of the base. So we have an HCl solution represented by this diagram, right? Primarily what we're concerned about is the number of protons in that solution. In the following diagrams, only the hydrogen and hydroxide ions that participate in the net ionic reaction are shown for clarity. So this is our solution, or unknown solution. We don't know what the concentration of this is. And so we take a known solution of hydroxide, and we use a burette. So this is graduated, and it'll tell us exactly how much of the sodium hydroxide we've added, and we know the concentration. So if we know that we added 0.050 liters of our sodium hydroxide, and we know the molarity of that. So let's just say it's 1.5 molar, which for clarity here, I'm going to write moles per liter. Then we can multiply. I forgot my calculator at home. So we can do 0.05 times 1.5. So we're multiplying there. Liters cancels. We get 0.075 moles of sodium hydroxide added. So let me zoom. Right, so okay. We're adding this hydroxide. We know exactly the concentration of that. As we add it into our unknown sample, right, every molecule of, well, I guess it does show, oh no, that is hydroxide. Right, so every molecule of hydroxide that we add enters the solution and combines with hydrogen. Right, so these are added in and combined with the hydrogens. And as they do that, we start using up all of the available hydrogens in that solution. And at some point we reach the equivalence point, where the number of hydroxide atoms that hydroxide molecules that we've added are combined with all of the hydrogen atoms that are available, and we use them all up. At that point, this is now, I don't know if we talked about pH yet. This is a pH 7 solution, so it's neutral. And for phenolphthalein, it turns pink as soon as you have a neutral solution. So that's how you know in a reaction or in a titration when you've reached that endpoint. And then you can say, well, if I added this much hydroxide, I know the concentration of that. and I added this many moles of hydroxide, then I know how many moles of hydrochloric acid, or how many protons really, were in this solution. So this equivalence point is usually signaled by an indicator, which is a dye whose color depends on the acidity of the solution. So how many protons are in the solution? And usually the concentration of one reactant, one of the reactant solutions is known and the concentration of the other is unknown, sorry. And the other is precisely known. So we'd know that out to several decimal places. And by carefully measuring the volume of each solution required to reach the equivalence point, the concentration of the unknown solution can be determined based on the concentration of the known. So here's what a real titration would look like. So as you add this sodium hydroxide to a hydrochloric acid solution, when the sodium hydroxide and the HCl reach stoichiometric property or proportions, so 1-to-1 ratio, the indicator changes to pink. Phenolphthalein is the indicator that we use most in general chemistry. It forms this nice pink color. And what you'll see actually as you get closer and closer to the endpoint is nothing will change for a long time. And then all of a sudden you'll see a little bit of pink, but as soon as you stop the sodium hydroxide adding into the solution, it'll disappear. But it'll stick around longer and longer as you get closer to the equivalence point. And it usually only takes a drop or two to go from clear to bright pink. So we have a titration of a 20 ml sample, 20 milliliter sample of sulfuric acid. Okay. Sulfuric acid solution of unknown concentration requires 22.87 milliliters of 0.158 molar potassium hydroxide solution to reach the equivalence point. What is the concentration in moles per liter of the unknown sulfuric acid solution? So always want to start with what you know or what you're given. So we have 20.0 milliliters of this H2SO4 solution. We have an unknown molarity. Again, capital M is molarity is moles per liter. So we have unknown molarity, H2SO4. We also have 22.87 milliliters of potassium hydroxide, and we know that concentration, 0.158 molar. So molarity most often is used as a conversion factor between moles and liters. So here, if we're going to write this out as a solution diagram, we're going to start with milliliters of potassium hydroxide, and we want to get to molarity. Yeah, we want to get to molarity of H2SO4. So we're going to have multiple steps in between. So let's see, let me see if I can do this in my head. I think that would be it. Yeah, so we have 3 steps in between. So usually, trying to give you these blanks, so you can try and fill them in before I fill them in. Usually when I look at this, I try to say, I have units of milliliters. based on the conversion factors that I have, what can I convert to? So in this case, well, actually, might need to draw out the reaction equation for this one, because we have H2SO4. Actually, you don't really need to draw out the reaction equation, but I'm going to do it so you can see this. Right? We write the ionizable hydrogens first. So if you have something like H2SO4, there's two hydrogens that are out front. Both of those are ionizable hydrogens, or hydrogens that we can that sulfuric acid can donate to the solution. So our products are going to be, as they always are, water and a salt. K2SO4 will be our salt. But because we have two hydrogens that we need to remove from H2SO4, we're going to need twice the potassium hydroxide. We're going to produce twice the amount of water. Okay. So what is our first step? We're going to go from milliliters of potassium hydroxide to we just want to match up our units here, because ultimately we are using a reaction equation to go from potassium hydroxide to the amount of sulfuric acid. So we always want to be working towards moles to get there. So our first step is going to be to convert to liters of potassium hydroxide. Once we have liters of potassium hydroxide, we can then use our molarity, 0.158 molar potassium hydroxide, which is in units of moles per liter. So if we can use that then, and we'll get moles of KOH. And then once we have moles of KOH, we have a reaction equation, then we can really find the number of moles of anything else in that reaction equation. But for this example, we're looking for molarity of sulfuric acid. So we're going to convert here moles of H2SO4. And then once we have moles of H2SO4, we have this volume of sulfuric acid. We can use that to calculate moles per liter, which is our molarity of H2SO4, which will involve converting that milliliters to liters. So if we have, we were doing it here, 22.87 milliliters, didn't leave enough space. You know, there's 1,000 milliliters in a liter. So now that we have liters of potassium hydroxide, we can calculate moles of potassium hydroxide using molarity, 0.158 moles per 1 liter. Now that we have moles of potassium hydroxide, we can calculate the moles of sulfuric acid. And based on our reaction equation, we have 1 mole of sulfuric acid for every 2 moles of potassium hydroxide. 1 mole H2SO4 for every 2 moles potassium hydroxide. So these are all potassium hydroxide. just didn't have enough space. And then we can divide by our volume of sulfuric acid in liters. So it's going to be 0.020 liters H2SO4. So if we multiply by 1 over the number, that's the same as dividing. And that should give us our answer. So 22.87 divided, well, times 0.158 divided by 1,000 divided by 2 divided by 0.02. So our molarity, if I punched everything into the calculator, right? Always run out of space. 0.09, my sig figs are we working with here? 3.903 molar H2SO4.
Professor K.
Yes?
How did you get 0.020 liters?
Oh, I did that one, ran out of space. But I took the 20 milliliters of H2SO4 and converted it to liters.
Okay.
All right. Oh. Well, we'll talk about these briefly. So don't worry about memorizing these for the exam. I'm not going to ask you a strong acid, weak acid on an exam. So strong acids, though, like hydrochloric acid, hydrofluoric acid. Hydrochloric acid is a strong acid. These are also strong electrolytes. So they produce lots of ions when you add them to solution. So HCl, when you add it to water, completely ionizes to H3O plus, I guess in this case, Cl minus. When you add hydrofluoric acid, we talked about equilibrium. Hydrofluoric acid plus H2O does not react completely. So if I was going to write these, actually here, let me write this. So for this top reaction, this is a really big forward reaction and a really small reverse reaction. So it pretty much entirely goes to these ions. When you add hydrofluoric acid, much fewer of those go and become ions, and they actually is closer to staying equal or into some kind of equilibrium where you've got a significant number of hydrofluoric acid in solution, as well as an amount of H3O plus F minus. So these are similar reaction rates at equilibrium. Or I guess, yeah, the relative amounts are about the same. So your strong acids, completely ionize. Your weak acids do not completely ionize. And actually, you can do a cool experiment with these where you take weak electrolytes and they have these, it's a terrifying contraption because it's a light bulb and you plug it into a socket and then it's got 2 electrodes and then you dip that into different solutions, which I'm sure there's some electronics inside to keep you from electrocuting yourself, but still. If you stick that light bulb into a solution of, or those electrodes into a solution of something like hydrofluoric acid, which is a weak acid, you'll get a dim light on that light bulb. If you take that and put that into the hydrochloric solution, it'll light up completely. That's part of why these are also called electrolytes, because they can conduct electricity. All right, so our strong acids ionize completely. So a 1 molar, so this is another way to indicate concentration using brackets like this. If we have a 1 molar hydrochloric acid solution, we'll have 1 molar hydrogen ions. Brackets means molar concentration of. So again, all right, simple arrow, complete ionization. Oh, this is exactly, yeah. Right, so you can take pure water, does not conduct electricity, but the presence of ions causes the light bulb to light up because it can conduct electricity. Which, because we're not covering this in extreme depth, saw a crazy YouTube video that explains that electrons don't flow through wires. And it's not the electrons that transfer the power, it's the magnetic and it's the electromagnetic field around the wire that actually transfers power, which is a little mind-blowing. So these are not directly ferrying electrons across this gap. They allow an electron or an electromagnetic field to set up between those 2 electrodes to transfer that power. In general, this will be something that will be helpful if you take Chem 20. These things like hydrochloric acid, hydrobromic acid, these are all strong acids. These are or not polyprotic. One of these is polyprotic. Monoprotic acids contain only 1 ionizable proton. So right, 1 for each of these. But we have, polyprotic ions or acids as well. Sulfuric acid being one of those is diprotic, so 2 protons. And you can tell because it has an H2 in front. You can have other solutions or other acids. So you get HC2, H3, O2 is acetic acid. So you have hydrogens here in the middle that are not ionizable, but then this one out front is. Weak acids don't completely ionize. So some of them do. You'll have some ions in solution, but not very many. And you can use a double arrow to indicate that partial ionization. Again, pure water doesn't conduct, but a hydrofluoric acid solution, the light will glow dimly. So the weak acids, hydrofluoric acid is the only binary acid that's a weak acid. And then the rest of these are things like acetic acid, formic acid, so organic acids, meaning mostly carbon. Sulfurous acid, carbonic acid, and phosphoric acid is actually a weak acid. Although in this class, we treat phosphoric acid as a strong acid. You can see that phosphoric acid has 3 hydrogens in front of the molecular formula, so it's triprotic. Yeah, and yeah, it's going deeper than this class goes. We can do this one though. So which of these is a weak acid? That's easy enough to see. There you go. So we've got hydrogens, hydronium and iodine in solution. So these ones look like they're right. None of these iodines have a hydrogen anymore. So that's a strong acid. We look at the second one. Looks like we have nitrate and we have hydronium. And so really what you're looking for on these is how many of these nitrates still have a hydrogen. And here it looks like none of them do. So it's also going to be a strong acid. On this last one, actually most of these, right? So if this is this is kind of a giveaway that it's showing you that like, look, this one has protons on it, right? So these, what is this, formic acid? So a lot of these formic acids still have the hydrogen on them. And in fact, this might be the only one that does that. So this is a weak acid. Yeah, we can do this. So if we want to determine the hydrogen concentration in a solution, we take 0.50 molar HCO2. So I'm just trying to think about how I want to handle this, because this is a weak acid, but let's just, for the moment, assume that it's a strong acid. Oh, no, maybe it's a strong acid. It's carboxylic acid. It's a strong acid. Okay, so how many ionizable protons do we have? All right, it's the number of protons that are out in front. Just have one ionizable proton. So that means that if this is a strong acid, then all of our protons are going to be hydrolyzed. They're going to be added to waters and hydroniums. So our concentration is actually going to be the same. And actually, let me write it like this. So we have one ionizable proton, one H plus for every HCHO2. So then our concentration will be the same, 0.50 molar H plus. Or this one looks like it wants H3O plus. So for this next one, 1.25 molar hydroiodic acid. Again, we have one H plus for every one HI. And our concentration is just the same. Oops. This last one is definitely a weak acid. So we have 0.75 molar hydrofluoric acid. Now in this case, almost none of them are going to be hydrolyzing. So while we do have one proton for every hydrofluoric acid, we could say that there's a potential of this many hydrogen ions. Instead, we're going to say that this is just less. Maybe this is the kind of thing that this question is looking for. It's going to be much, much less than 0.75 molar HF. Although you can probably imagine, depending on how well you remember the equilibrium stuff that we covered, if you knew the equilibrium constant for this, we could plug this molarity into an equation and figure out how much hydrofluoric acid would be at equilibrium, or how many hydronium ions would be at equilibrium from this amount of hydrofluoric acid. So strong bases are very much the same as strong acids, where they completely dissociate in solution. Unlike the polyprotic ions that we talked, or polyprotic acids that we talked about, diprotic or triprotic, which ionize in steps, bases ionize all at once. So strontium hydroxide will completely ionize into strontium and hydroxide ions in one step. All right, so if we add our sodium hydroxide, completely dissociates. All right, all those ions are separated. Weak bases are kind of the same as weak acids. The most common weak bases produce hydroxide by accepting a proton from water. So doing this indirect formation of hydroxides. Boron is one. Oh, sorry, boron. B is generic for a weak base. So we have B, which is our base, accepting a proton from water to create these hydroxide ions. Ammonia is the one that we looked at earlier as well. Accepts a proton from water to become NH4 from NH3, and then we get our base. So we add this into a solution, one of these protonates to give us one hydroxide. So organic amines, so really all of these organic amines are similar in sort of function to ammonia. They're all doing the same thing. They have this nitrogen, and so each of these has these nitrogens, which are picking up the hydrogen from the water to give us our hydroxides. The only one that's not in here is bicarbonate, but that's HCO3. And again, is picking up a hydrogen from water to make that hydroxide. All right, so let's try and do this like that last one. So this is a strong base. What's our hydroxide concentration going to be if it's a strong base? Is it going to be the same or less than? It's going to be the same, 0.55 molar. Sorry, not 0.55, because there's two hydroxides. It's going to be 0.110 molar hydroxide. And that's because if we want to write this out, we'd do so we get 2 OH minus for every 1 BaOH2. I mean, this question comes down to what is a weak acid, what is a strong base? Again, not going to ask you those specific questions about weak acids and strong, weak and strong acids, weak, strong bases. But if this is a weak base, what is our concentration going to be this, or is it going to be much less than that? But because it's a weak base, it's going to be much, much less than 1.05 molar. And if sodium hydroxide is a strong base, what's our concentration going to be? Because it's a strong base, it hydrolyzes completely, so it's 0.45 molar sodium hydroxide. Water is amphoteric, acts as either an acid or a base. Even in pure water, actually, you get water acting as an acid and a base with itself, which is called self-ionization. So they'll be swapping hydrogens back and forth. And the self-ionization reaction occurs only to a very small extent. So you get equal but small concentrations of hydroxide and hydronium. In pure water, both of these concentrations are equal to 1 times 10 to the negative 7. Now this will be important because this is leading into how we calculate pH, which is something that I will give you on the exam. The whole idea of strong acids, weak acids, don't worry about that. This is key for calculating pH. So the ion product constant for water is, and this is based on equilibrium expressions that we talked about before. So if our reaction is H3O plus, sorry, it would be H2O. Right, we're gonna get this auto ionization into H3O plus and OH minus, so I guess it would be 2 waters. So if we wanted to write out an equilibrium constant for this, water here is a liquid. We leave liquids out, but these are both aqueous. So it's products over reactants. So K is equal to the concentration of H3O plus times the concentration of OH minus. And that's exactly what this is. So this is not just K, but this is also KW. And that's equal to 1.0 times 10 to the negative 14. So in a neutral solution, these are equal to each other. They're very, very small concentrations, right? 1 times 10 to the negative 7 is teeny tiny, but you have 1 times 10 to the negative 7 of hydronium and 1 times 10 to the negative 7 of hydroxide. And those are in units of molarity or moles per liter. So for a neutral solution, these are equal. Then in an acidic solution, that's any time that the concentration of our hydronium, H plus, or yeah, which is essentially H plus, is greater than 1.0 times 10 to the negative 7. And our hydroxide concentration is less than that. Because if we add more protons to solution, those protons get added to hydroxide to form, well, through water, hydronium. And then in the basic solution, it's the opposite. So we have less of the acid, right? So less than this neutral concentration, and more of hydroxide. But for any aqueous solution, this is the case. If you multiply the two concentrations together, it's going to be 1 times 10 to the negative 14. So you can have a scale like this. And I'm sure Timberlake, your guys' book has this, or the book that we have for this class, I should say. If we're looking at whether something's acidic or not, this is our concentration. As that concentration, this is the one that's a little bit counterintuitive at first. Times 10 to the negative 7 is smaller than times 10 to the negative 6. And so on down to the 0. And then if we move down to this hydroxide scale, we can see that this concentration is getting smaller as we move towards acidic, and the concentration gets higher, greater, as we move towards basic. All right, so if we calculate the hydroxide or hydronium concentration in each of these solutions and determine whether the solution is acidic, basic, or neutral. And really the key for this is that Kw equals 1.0 times 10 the negative 14, which is equal to the concentration of H3O plus times the concentration of OH minus. So really, we can just take these numbers, plug them in, and solve for the one that we want. So these are all hydroxide concentrations. Now, actually, before we even do that, is this acidic or basic based on the OH concentration? We have 1.5 times 10 to the negative 2. We go back to our scale, times 10 to the, so we're looking at hydroxide. If this is times 10 to the negative 2, it's a basic solution. But we want to calculate our hydronium concentrations. So like 1.0 times 10 to the negative 14 equals the hydronium concentration that we want, although the order of these doesn't matter, times, and I'm going to sub in hydroxide concentration. So 1.5 times 10 to the negative 2. So then we'll get 1.0 times 10 to the negative 14 divided by 1.5 times 10 to the negative 2. So then our hydroxide concentration will be 6.67 times 10. What was that, to the negative 13? Yeah, times 10 to the negative 13. So we can go back to our scale and say, okay, we're looking at H3O plus at times 10 to the negative 13, which is a very, very small number. Oops. So H3O plus times 10 to the negative 13. You'll notice that it is right across from times 10 to the negative 2. So this is a basic solution, whether you look at it from the acid or the hydroxide, or the acid or the base. So for the rest of these, it's going to be the same thing. 1.0 times 10 to the negative 7. Oops, did that backwards. Hold on, put that over there. 1.0 times 10 to the negative 14. So this one you can do, well, if you know about how to multiply and divide exponents, this one's easy. So anytime you have 1 as your coefficient in front of your times 10 to, you can add or subtract them. So this is 1.0 times 10 to the negative 7 H3O plus. So if both these concentrations are times 10 to the negative 7, then we have a neutral solution. Do this last one real quick, but it's exactly the same. So for these kind of problems, converting between hydroxide and hydroxide and hydronium, it is more formulaic than it is doing like a stoichiometry problem, converting those units. You just use this equation when you have concentrations. So then we'll have H3O plus times 8.2 times 10 to the negative 10. And I will say that probably the easiest place to make mistakes here would be typing things into the calculator. So this is 1 times 10 to the negative 14. And we're going to divide by 8.2 times 10 to the negative 10. Oh, couldn't you give it to me in scientific notation? It's 1, 2, 3, 4, 5. So 1.2 times 10 to the negative 5. So because this number is greater than times 10 to the negative 7, this would be acidic. Oh, I didn't write that for any of these. Acidic, neutral, basic. All right, so that one is important to know. So that's all fine, that's good. You can use these in these concentrations if you really want to write out times 10 to the whatever a million times. There's an easier way though to do acid and base concentrations, and that's pH and pOH. So looking at pH, pOH, we have on this pH scale, pH 7 is neutral. pH 1 would be strongly acidic, pH 14 would be strongly basic. So as the pH number gets smaller, your concentration is actually getting greater. So this is when you like pH balanced water or pH neutral basic water, which is meaningless. You have stomach acid, like it doesn't do anything. I guess unless you have acid reflux, then maybe drinking a pH 8.5 water would like help with that. This pH scale is a logarithmic scale. So the way we get to the pH scale is pH 4 is a result of the negative log of 10 to the negative 4. So if we took negative log of 1 times 10 to the negative 4, the answer to that is 4. It's very easy to do. You go back and forth when your coefficient here is 1 or when your log is a whole number, because this just becomes the negative exponent on your times 10. What this means though is when we're moving from pH 4 to pH 3, it's not one more concentration unit greater, it's actually 10 times greater. And then going to 2 is 10 times that again. So every time we change one pH unit, we're multiplying that by 10. So times 10 to the negative 4, negative 3, negative 2. Explain logarithms. I don't know if I can explain logarithms necessarily, except for how to use them practically. One of the things that you need to know, I'm just trying to get my calculator here. There are different logs. So when we're looking at, let's say, negative log of concentration, so 1 times 10 to the negative 7. This log, log, means a base of 10. So on a calculator, you'll see something like, and I can't use the pointer here, but how can I indicate this? So we start here at 8 and then move up, right? There's log 10. Well, there we go, that works. I don't know if you can see that on the projector though. So log 10, there's also natural log, that's log base E, which E is its own special number, gives me an error. There's also log base 2. So if you're using your calculator, and your calculator has 2 buttons, it has LN. Well, actually, some of them have them on the same button. It'll be LN or LOG. Make sure you're using LOG. So when you take the log of something, it's asking, I start to think about this. So the log of this is negative 7. So the question for log base 10 is what power do I have to raise this number to? Actually, it's asking what power is this number raised to? So you're just taking this, moving it over here. Where things get a little bit squirrely is if we do log of 1.5 times 10 to the negative 7. Now we need a decimal number because this is not a whole log. So if I do 1.5 e to the negative 7, okay, and then we want the log base 10 of that, it's actually going to be negative 6.82. And if we take our number, or if we take this and we want to go back to our original concentration, we can do that by taking 10 and raising it to this power. So if we take this and raise it to negative 6.82, so I do 6.82 negative. Actually, wait, how do I do it on this calculator? We need to do 10. Okay. So it's 10 raised to the, I wish I had my calculator. 10. Nope, I did 10 raised to the 10. Okay, I got it. 6.82, right? Negative 6.82. If we raise that, I'm gonna hit this 10 to the X button. It'll give us, and you'll see there's some error here because of rounding. This is equal to 1.51 times 10 to the negative 7. So started here, and we did the log base 10 to get this number. And then we took this number and we said 10 raised to this power gives us this, which is very close, but because we rounded in the middle, it gets some rounding error. So we use the negative log because we want whole number, or we want positive numbers. So that when we do this math, instead of negative 6.82, we get positive 6.82. So the thing to remember with pH and with logarithms really is that to go from a concentration to pH, you do negative log of the concentration. If you want to go from pH to back to your concentration, you're going to do 10 raised to the negative pH. So you're always flipping that sign as you go back and forth. Logarithms are weird, but they make this math easy. They make the rest of the math easy. This is not so hard once you've got it down on the cheat sheet. Highly recommend. Actually, I think I'll do that for the final. You guys can make a cheat sheet because I think that cheat sheets are an excellent way to study. Okay. Do you need more time on that one? You're good? Okay. Very quickly, let's do these actual pH calculations now. So we want to calculate the pH of this solution. pH is equal to negative log of the H3O plus concentration. So negative log of 9.5 times 10 to the negative 9. So if you have a phone calculator, it's going to look very similar to this. But I'm at 9.5 e to the negative 9 equals, and then I'm going to do the log, and then I'm just going to take the negative, or you can multiply this by -1 if you want. to get an answer as 8.02. So very similar to our scale of, -7 or 10 to the -7 is neutral, 10 to the -8 is acidic. So this is 9.5 times 10 to the -9. Our pH though is 8.02. So this is going to be basic. For this next one, again, it's just the negative log, 6.1 times 10 to the -3. So 6.1 e to the -3, log base 10 times -1. So 2.21 will be your pH. And you can see, especially with these examples, how you can't just use the exponent to figure out what your pH is going to be. So 9.5 times 10 to the -9 is actually really close to being 10 to the -8. So we get 10 to the -8.02, or pH of 8.02. This one is 6.1 times 10 to the -3. So we end up actually with a pH of 2.21. So you really do have to, unless you're like a savant for doing logarithms in your head, really need to do the calculations. I was probably going to talk about pOH next. Oh, well, could have talked about this, but if you want to go back from your pH to your concentration, then it's just 10 raised to the negative pH will give you your H3O plus. There's one thing that I want to get to before though. So pOH is the same thing. You just have to start with the negative log of the OH concentration. Oh, derive the relationship. Okay. Let me do that. Right. So if pOH is the same thing as pH, just using hydroxide concentration, we can do this. So we can say Kw, remember that's our ionization constant for water, or it's an equilibrium constant. That's equal to the concentration of H3O plus and OH minus. So this is, we can actually put numbers to these. For a neutral solution, this is times 10 to the -14. This is 1 times 10 to the -7 molar H3O plus times 1 times 10 to the -7 molar OH minus. So we can turn these into pHs and pOHs as well. We can take the negative log of each of these. And this is going to be 14 is equal to, and this is a rule of logarithms. If you take the log of A times B, that's equal to the log of A plus the log of B. So here, if I take the logarithm of this whole thing, we'll get 7 pH plus 7 pOH. So for a neutral solution, And actually, for any solution, the pH plus the pOH is equal to 14. In a neutral solution, it's 7 and 7. If you had a basic solution, so we do, so let's call this one basic, right? Our pH would be higher. So let's say we have a pH of 10. Our pOH would be 4. For an acidic solution, it's 14. Then our pH now needs to be less than 7. So we'll just flip it exactly. So pH of 4, our pOH would have to be 10. So pH plus pOH always equals 14. And because of that, you can use it to convert between the two. You can also use kW, but you got to write everything out times 10 to the negative numbers for the small concentrations. So we can do that, but oh yeah, we're not doing buffers. Nope. Okay. I want to, there's one last thing. Add a page in here. Okay. So let's say we have a solution that is pH 3. What is pOH? So the key to this one, again, is that pH plus pOH equals 14. So we can say 14 equals our pH 3 plus our pOH. So then we can just subtract 3 from both sides and get 11 is equal to our pOH, and vice versa. And then if we wanted to convert this pOH to molarity, which is the raw concentration, we would do 10 raised to the negative 11, which would be 1 times 10 to the negative 11 molar OH minus. So there's only really, what is that? Like 2 or 3 different operations that we do in converting acid or base concentrations. There's the negative log. I'm just going to put brackets in here, right? And that's going to give us, pOH or pH, depending on which concentration we put in there. And then there's 10 raised to the pH or pOH, sorry, negative, which will give us back our concentration, whether it's pH or OH, doesn't really matter. And then really the third thing is that 14 is equal to pOH plus pH. And then by extension, you could derive from that 10 to the minus 14 is equal to the concentration of OH minus times the concentration of H plus. So that's kind of the whole summary of everything that we've covered in terms of acid and base calculations. So that's definitely something that's going to have a few questions like that on the exam. Just convert from pH to pOH, convert from concentration to pH, that kind of thing. And yeah, we're not covering the rest of the stuff in this chapter. And we do have a lab tomorrow, an actual lab where we get to mix chemicals together. So that'll be fun. I think it's the reactions lab. I haven't looked. I'll send out an announcement for exactly which one it is. Any questions? Anything? This is like the last lecture, so I don't know. Maybe I'll send out a survey or something, and if we want to have next week, like show up here, and if you want to ask questions about things, we could just have like a study session, or yeah. We don't have to, and then I don't have to get up at 8 or get up and be here at 8:30. All right, let's see. We got to Canvas. I'll miss some chats. Yeah, I mean, we could either do it here or we could do it Zoom even, or yeah, just a review session to try and cover every topic briefly.